Welcome to WikiPodcast. All right, welcome back to the deep dive. Today, we're getting into a force that's literally everywhere, all around you, all the time. It holds you together. It lets you hear this podcast, and it powers, well, pretty much everything in the modern world. We're talking about electromagnetism.
That's right. And for this deep dive, we've looked at sources covering the history, the physics, and the, frankly, incredible impact of this fundamental force.
So our mission today is what? To really understand what it is.
Basically, yes. To uncover what electromagnetism is at its core, trace how we humans figured it out over time, and really show you just how much it shapes our daily lives.
Okay.
It's one of the big four fundamental forces, right up there with gravity and the nuclear forces, and it's responsible for so much of what we just see as reality.
Okay, so let's start right at the beginning then. What is electromagnetism? The sources say it's about how particles with electric charge interact through fields.
Exactly. It sounds a bit abstract, maybe, but it breaks down into two things most people have heard of.
Right, electricity and magnetism.
Precisely. It's a unified idea, but it came from studying those two things separately. First, you have electrostatics.
Okay.
That's the force between charges that are just sitting still. Static, it's the basic stuff, like charges repel, opposites attract.
The classic positive and negative thing?
And the strength of that push or pull. That's described by Coulomb's law. It basically says the force depends on how much charge you have and how far apart the charges are. Closer means stronger.
Got it. Static charges pushing and pulling. So the other part is magnetism, when things are moving.
Exactly right. Magnetism pops up when those charged particles are moving relative to each other.
Oh, okay.
That's described by other laws, like Ampere's force law, think forces between wires with current, and the Lorentz force, which is the force on a single charged particle moving through a magnetic field.
So electromagnetism is the whole package. Static attraction, repulsion, and the magnetic stuff from moving charges.
It's the unified picture, yes.
And the sources made a point here that I found, well, kind of mind-blowing. They say this force is responsible for almost all everyday chemical and physical stuff we see.
It's profoundly true. I mean, think about atoms. What holds them together?
Electrons in the nucleus.
Right. It's the electromagnetic pull between the positive nucleus and the negative electrons swirling around it. And then how do atoms join up to make molecules?
Chemical bonds.
Also, electromagnetism, creating those bonds. The sources even mention magnetic interactions play a role in chemistry, too. So yeah, the very structure of matter, from atoms to the huge molecules essential for life, it's all built on electromagnetism.
Wow. So the fundamental stuff that makes up everything is held together electromagnetically. Okay, but then there's that other point. Friction. Contact forces. You're saying those aren't fundamental?
That's a key insight from the material, yeah. All those forces we experience, daily friction, the resistance when you push something, tension in a rope, they aren't fundamental forces themselves.
Yeah.
They're actually macroscopic effects derived from the four fundamental forces. And electromagnetism is doing a lot of the heavy lifting there.
So when I push on a wall and feel it push back.
That's the electromagnetic repulsion between the electron clouds of the atoms in your hand and the atoms in the wall. They don't want to get too close. So contact is really just very short-range electromagnetic interaction.
Okay, that changes how you think about just touching things.
Yeah.
So how did we start figuring this out? It sounds super complex, but the sources say people noticed something was going on way back.
Oh, millennia ago. We're talking ancient civilizations, 5,000 years back. China, Mesoamerica, Egypt. They knew about magnetic rocks, lodestones or magnetite.
Yeah.
They saw lightning, obviously. And they noticed static electricity like rubbing amber and making it pick up little bits of stuff. They didn't know why, but they saw these weird forces.
And then you get thinkers like Thales and Miletus. Way back, 600 BCE, he was actually playing with this stuff.
Yeah, he experimented with rubbing amber for static effects and looked at magnetic rocks. Apparently, he even wondered if there was some kind of link between them, just an intuition, centuries early.
Amazing, but the real science, the math, they came much later, right? 18th, 19th centuries.
That's when the quantitative understanding really kicked off. There were hints, though. The sources mention a Dr. Cookson in 1735 reporting that lightning hit a house and magnetized steel knives and forks inside.
Whoa. So lightning created magnetism.
Seemed like it. An early accidental clue linking electricity and magnetism.
And wasn't there someone in Italy around 1802, Romagnosi?
Yeah, Domenico Romagnosi, yes. He reportedly saw that an early battery, a voltaic pile, could make a compass needle move. Potentially the first observation of current causing a magnetic effect. But sadly, his work didn't really get noticed then.
Ah, too bad. So the big recognized breakthrough came later.
It did. 1820, a Danish physicist, Hans Christian Ørsted. The story goes he was setting up for a lecture and noticed when he turned on an electric current in a wire, a nearby compass needle jumped.
Yes. Deflected. Because of the current.
Exactly. The electric current was creating a magnetic field. Nobody expected that. It was a huge discovery.
It must have been a real, wait, what moment. These two separate things are connected.
Absolutely. And Ørsted's discovery just lit a fire under the scientific community. People jumped on it. One key figure was André-Marie Ampère in France.
Ampere, right. Heard of him.
He took Ørsted's finding and very quickly did brilliant experiments and developed the mathematical laws describing the forces between wires carrying currents.
So Ørsted shows current makes magnetism. Ampere provides the math for how it works.
That's a good summary, yeah. It was the real beginning of seeing the connection, but they were still often treated as related but distinct phenomena, not quite unified.
Like two puzzle pieces, fit, but you haven't quite snapped them together yet.
Nicely put. And snapping them together, the grand unification, the sources point to one person above all.
That would be Maxwell. James Clerk Maxwell.
The man himself, Scottish physicist. In 1873, he published his treatise on electricity and magnetism. It was monumental. He took everything known, Coulomb, Ampere, Faraday's work on induction, all of it, and synthesized it.
Into just 4 equations, that's what I read, Maxwell's equation.
Just 4 elegant equations. It's incredible.
Yeah.
And they perfectly described everything known then and predicted things nobody had dreamed of.
Okay, so what were the main known things they covered?
The sources highlight 4 key effects. 1, electric charges interact, likes repel, opposites attract, that's Coulomb's law territory.
Okay.
2, magnetic poles attract and repel, but crucially, they always come in north-south pairs, no magnetic monopoles.
Right.
3, electric currents create magnetic fields around them, that's Ørsted's discovery, generalized. And 4, this was huge, based on Faraday's work, a changing magnetic field creates an electric current, or more accurately, an electric field. It's called electromagnetic induction.
Okay, so those 4 tie up all the known experimental results.
Yeah.
But you said predictions. What was new?
This is the stunner. When Maxwell worked through his equations, he realized they predicted that changing electric and magnetic fields could generate each other, propagating outwards through space as waves.
Waves, like ripples.
Exactly. Self-sustaining electromagnetic waves. And when he calculated the speed these waves should travel at,
Don't tell me.
it matched the known speed of light perfectly.
No way. He calculated the speed of these theoretical waves, and it was c.
Precisely, which led him to the absolutely radical idea. Maybe visible light is one of these electromagnetic waves. He unified electricity, magnetism, and light in one go.
That's unbelievable. And was he right?
Spectacularly right. Later experiments confirmed it. And it turned out visible light is just a tiny slice of a vast electromagnetic spectrum. Radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, all the same thing.
Just electromagnetic waves vibrating at different frequencies.
Exactly. All traveling at the speed of light in a vacuum. It's arguably one of the greatest unifications in the history of science. Static cling, magnets, lightning, sunlight,
Right.
all connected.
Wow. Okay, so that's the classical picture Maxwell gave us. Incredible. But the sources also mention modern physics, relativity, and quantum mechanics. How did they change things?
Well, interestingly, Maxwell's classical theory actually helped inspire one of those revolutions.
How so?
The fact that Maxwell's equations demanded the speed of light be constant no matter how you're moving, that was a major clue for Albert Einstein. It was a key ingredient in his development of special relativity in 1905.
Ah, so EM pointed the way to relativity.
In a sense, yes. And special relativity then shed new light back onto electromagnetism. It showed that electric and magnetic fields aren't truly separate. They're different facets of a single entity, the electromagnetic field.
What do you mean facets?
It means what one person sees as just an electric field, someone moving relative to them might see as a mix of electric and magnetic field. They kind of transform into each other depending on your perspective, your frame of reference.
So electricity can look like magnetism and vice versa, depending on how you're moving.
Weird.
It really is. It cemented their inseparability. Then came quantum mechanics, the rules of the very small. Electromagnetism had to be updated for that too.
And that led to?
Quantum electrodynamics, or QED. It's the quantum field theory of electromagnetism. It takes Maxwell's ideas but makes them work with the quantized nature of energy and matter.
Quantized, meaning discrete packets.
Exactly. In QED, the electromagnetic force isn't transmitted by smooth fields, but by exchanging discrete particles, little packets of energy called photons.
Photons, particles of light.
Particles of light, and indeed the carriers for all electromagnetic interactions. When charged particles interact, they're essentially tossing photons back and forth.
So from separate forces to unified waves to relative aspects of one field to particles carrying the force. What a journey of understanding.
It really has been. And this deep understanding isn't just for physicists. The sources are emphatic. This knowledge powers the modern world.
It really does, doesn't it?
Yeah.
You just look around, electrical power generation.
Mostly electromagnetic induction, generators spinning coils in magnetic fields.
Power lines, transformers.
All electromagnetism. The whole grid is a giant electromagnetic system.
Lights, heaters, speakers, microphones.
Yep. Converting electromagnetic energy to other forms, or the reverse.
Communications, radio, TV, Wi-Fi, your phone signal.
All electromagnetic waves. Maxwell's waves carrying information across space, fiber optics too, guiding light waves.
Computers, the chips, the memory.
Controlling electron flow, storing data magnetically, sending signals. Fundamentally electromagnetic.
And manufacturing, motors. The sources mentioned things like electrolysis, electroplating,
Yeah.
electric motors, everything from cars to blenders.
Absolutely. And specific examples like smartphones and MRI machines really drive it home.
Yeah, talk about those. A smartphone seems packed with this stuff.
Totally. Battery chemistry relies on electromagnetic bonds. The touchscreen uses electric fields. Antennas send and receive radio waves, pure EM. Microchips manage electron flow. It's an electromagnetic marvel in your pocket.
And MRI machines.
They use incredibly strong magnetic fields and radio waves, more EM radiation, to get detailed images inside the human body by interacting with protons. It's amazing medical technology, built entirely on understanding electromagnetism.
It makes you realize that all the engineering behind circuits, magnets, semiconductors, it all stems from figuring out this one fundamental force.
Precisely. Our ability to design and build virtually all modern technology traces back to understanding electromagnetism.
It's invisible most of the time, but its effects are just
Mm.
everywhere, powering everything, connecting everyone.
It's fundamental.
So thinking about this whole story, from ancient wonder about magnets to Thales to Ørsted and Ampere connecting things, then Maxwell's incredible unification revealing light, and finally relativity and quantum mechanics refining it. It's more than just learning about one force, isn't it?
It really is. What strikes me, thinking about the sources, is how digging deeper into this one force has repeatedly forced us to completely rethink our understanding of the universe, space, time, energy, matter, how it all fits together.
Yeah. Makes you wonder, what's the next big shift in understanding this force going to reveal?
That's the exciting question, isn't it?
Thanks for listening. Write us your opinion in the comments on how the history of electromagnetism shows science building on itself. Subscribe to the channel to help more listeners reach our episodes. Thank you and have an amazing day.